Here's the second part of this section, moments and balancing. What we need to do in this section is to know what we mean by a moment. We need to be making sure that we don't confuse that word with momentum. It's really got nothing to do with momentum at all. We need to be able to calculate the size of a moment, and crucially we need to be able to work out whether something will balance, and for slightly trickier calculations work out what we've got to do to make it balance. So first thing we need to do is to decide the basic principle we're working on here. If you've got a paint tin, you can never stick your fingers under there to open it up. You always have to get a screwdriver. So here's some screwdrivers. Which one's going to be best to open it up? Well, when we do this, what we've really got is a pivot here. We've got a force applied under this lip, and we've got a force that we push down with our hand over here. So which one's going to be best? Well, we know really that we're going to use the longest one, because the longer this is, the more of a lever we've got, the more turning effect we can produce. So that's the basic principle. We need to try to establish how we're going to actually do the physics behind this. Another little example to get you thinking: if you hold a mass on a, I think we've got some kind of snooker cue or something here. If you can hold it like that, does that mean you can lift that mass? Well, not necessarily, because as you move it further away, it seems as if it gets heavier. It doesn't really get heavier, of course. The weight of this thing stays the same, but you need to produce a bigger and bigger force with your hand. What you've really got here is a pivot, which is somewhere inside your hand over here, and then you're applying a force here quite close to the pivot, and the further this force, this mass gets away from the pivot, the bigger turning effect it has. So of course, being physics, we need to try to put some numbers so we can do a proper analysis of this, and this is how we do it. We'll say the turning force, which we also call the moment, which is measured in Newton meters, or Newton centimeters is sometimes more convenient for us to use. Notice this is not newtons per meter, this is newtons times meters, or newtons times centimeters. It's equal to the size of the force, which we measure in newtons, times the distance from the pivot, measured either in meters or centimeters, whichever is convenient, as long as we're clear which one we're using. Either one is fine. So the turning effect of a force is called its moment, and the size of the turning effect is determined by the distance from the pivot the force is applied. So if I've got a 45 centimeter long spanner and doing a wheel nut with a 40 Newton force, it's really simple. All you've got to do is the force times the distance. That's 40 times 45, that comes to 1800 in Newton centimeters. If it's a 20 Newton force, 1.6 meters from the end of a brush, okay, then it's 20 times 1.6, 32 Newton meters. Okay, make sure you're confident with those, because we're using that all the way through. And the other thing we need to understand is clockwise and anti-clockwise moments. So you'll be familiar with the idea of using forces in two directions, and if there's a bigger force right or a bigger force left, that'll tell you which way it'll go. We talk about resultant force. Well, moments are a little bit different, because here's two boys trying to play on a seesaw, and both the forces are going down. So it would be useless for us to talk about a downwards force and a downwards force. Okay, the point about this is they're trying to make it turn in opposite directions. So here's Mark weighs more. Here's his weight. He's trying to make this side go down. This means the system will rotate this way. That's clockwise. Here's Tim with a smaller force, the same distance from the pivot. He's trying to make it go this way. Okay, but we should be able to see that this will have a bigger effect. So Mark's end's going to go down. Poor little Tim's going to be stuck up, waving his legs around in the air. Here's some numbers to analyse this. Okay, what we've got is on the left-hand side, this is trying to make this pivot turn trying to make the seesaw turn anti-clockwise. 300 newtons, 1.5 meters from the pivot, 300 times 1.5 gives this a moment of 450 newton meters anti-clockwise. Here's the force trying to make it go clockwise, 600 times 1.5, 900 newton meters. Obviously 900 is more than 400, so there's a bigger clockwise moment than anti-clockwise moment, so the seesaw is going to rotate clockwise. Just a little thing that they sometimes love to ask: this system can't be in equilibrium with just those two forces, because you'll notice they're both going down. Why isn't the whole thing moving down? Well, we need a pivot. So there must be a force at the pivot. Remember that in order for there to be no resultant force, the downwards forces must add up to the upwards forces. We've got a total of 900 down, so there must be a 900 Newton force up at the pivot. But notice the moment of this force is 0 because its distance from the pivot is 0, so it's 900 times 0, which is 0. Is there a way of making these two boys be able to play on the seesaw? Well, there is. You just have to move the heavier boy closer to the pivot. How much closer to the pivot? Well, the anti-clockwise moment we've already done is 450 Newton meters. So to make it balance, this 600 times d, the clockwise one, must be equal to that. So 450, the anti-clockwise moment, must equal 600d, the clockwise moment. A little bit of algebra gets us to 0.75 meters. You can always go back and check. 600 times 0.75 is 450 Newton meters each way. Okay, just to finish off, a little bit of practice just to see if we can do them. Might be worth pausing the video here and just seeing if you can do these rather than just listening to me telling you. So here's the first one. 7 newtons, 40 centimeters from the pivot, has got to balance this weight on the other side, W, 20 centimeters from the pivot. It is a question of ratios, but there's a terrible temptation to think this will be 3.5 because it's half the distance, but you're doing it the wrong way if you do that. Okay, if it's half the distance, it's got to be twice the force. Better to do it mathematically and play safe. So we've got 7 times 40 is the anti-clockwise moment. We've got W times 20 is the clockwise moment. Doesn't matter that it's in centimeters because we're using centimeters both sides. 7 times 40 is 280. W times 20 is 20W. 280 divided by 20 gives us a 14 Newton force. Notice 14 twice as much as 7 because the distance is half as far. Okay, here's a second one. That one's really just the same, just for you to practice. This is the question where a lot of people go wrong. They love to give you a lot of different distances and you have to work out which ones you actually need to use and sometimes to add them together. So if we're working out the anti-clockwise moment here, 2 newtons, but not 2 times 20 because it's the distance from the pivot. Here's the pivot, so the total distance to the pivot is 30. So we get 2 times 30 plus 4 times 10 is W times 40. Okay, that's 60 plus 40 is 100, is 40W, 2.5 newtons. We'll balance out those two. Same sort of calculation with the last one, 2 times 40 centimeters from the pivot. So just be careful that when you're doing the distance, you don't just look for any old distance, you're looking where's the force, where's the pivot, what's the distance between those two objects.